Good morning, students. This is KG Misra. Okay, and I have come with the new topic. Okay, for class 12 in chapter electric potential and capacitance. Okay, that today's topic is the loss of energy in redistribution of charges. Okay, uh, see when actually we no. Suppose there is a conductor or a capacitor which is charged. Okay, and there is another conductor or capacitor, okay, which is maybe charged or may not be charged, okay, and suppose you are going to connect them both together, then what will happen? Obviously the conductor or the capacitor which has got the higher potential, okay, and suppose another has got the lower potential, then the charge will be flowing from the conductor or the capacitor at higher potential to the conductor or capacitor at lower potential, okay, and this flow of charge will continue till the both acquires a common potential, because potential of one will keep on decreasing, potential of another will keep on increasing. That already we have discussed, and we have got the expression for common potential. Now how their energy gets affected due to this, that's what we are going to discuss in this, okay. So this is the chapter, this is the topic, the loss of energy in redistribution of charges, okay. Now suppose we have got a capacitor, okay. uh, Let us take, okay, uh, let us consider a capacitor. Capacitor of capacitance C1, okay, potential V1, okay, has charge Q1, okay. So let us consider a capacitor of capacitance C1, comma, potential V1, and has charge Q, and has charge Q1, okay. Now what we can write from here? See, can we write Q1 is equals to C1 V1? This we can write. This is equation 1. What else we can write? Can we write the energy in that stored in that capacitor is how much? Let it be U1, and that is half C1 V1 square. This is our question 2. Okay, that's what the information we get from this. Okay, now we have to consider another capacitor. Okay, let us consider another capacitor okay of capacitance C2, okay, comma, potential V2, and has charge Q2. Then what we can write for this? In the same way, can we write Q2 is equals to what? Q2 is equals to C2 V2. This is our equation number 3. Okay. Now, what about the energy of this capacitor? The potential energy stored in the capacitor, we can write U2. U2 is equals to how much? Half. Okay. C2 and V2 square. Okay. So energy is how much? U2 is equals to half C2 V2 square. Okay. And we can mark it equation number 4. Okay. I think it's not clear, so I will write it again. Okay. Then writing here, it's better to draw and write. So we got this expression. Okay, for charge for the second capacitor. Now I have to write the expression for the energy, because there is very less space, so I can write here so energy stored, that is U2 is how much? That is half C2 V2 square. That is equation number 4. Okay, got it? Now when these two capacitors are connected, comma, then after some time they acquire they reach a common potential. V. Okay. So their energies so their potential energy is okay. So their potential energies are U1 dash. Why U1 dash? Because there is change in energy, no? Because the potential has changed. So what we can write? Potential energy stored in first capacitor is how much after getting connected? That is U1 dash, that is equals to half C1 V square. Why V? Because it's common potential, okay, which they acquire. And second we'll have U2 dash, that is equals to half C2 V square. Okay, very nice. Now what is the total initial potential energy of the combination? So total initial potential energy of the combination, let it be UI. UI is what? U1 plus U2. Okay, what is the value of U1? It is half C1 V1 square. What is the value of U2? It is half C2 V2 square. Okay, so can we take half common from there? Obviously we can take half common. We will get C1 V1 square plus C2 V2 square, and that is our initial. I for initial potential energy of this system. Okay, so we can mark it equation number equation number 5. Okay, so we got this expression for total initial potential energy of the system of two capacitors or two conductors. Okay, because you know capacitors have got the capacitance, even the conductors also have got the capacitance. Okay, we have found the capacitance of a sphere already, no, in the beginning of capacitance. So we got this expression. Now what about the total final potential energy stored in the system of two capacitors? So for final energy, what we have to do, we have to add U1 dash and U2 dash. Okay, so what we can write, see, final potential energy, that is we can write UF, it is total final potential energy, and that is U1 dash plus U2 dash. And what is U1 dash? It is half C1 V square. What is U2 dash? It is half C2 V square. Again we can take half common, and we can take V also common. So C1 plus C2, here V square is there, that is UF. But what is this V? It is a common potential, and we know that common potential is what? It is C1 V1 plus C2 V2 by C1 plus C2, that we have done in the last class. Okay, so we have to use this value over here. Okay, so now we can use this value. I have to rub this out first. So we can use this value. We will get final potential energy of the system. How much? Half C1 plus C2. And see, V square is there. This is value of V. So we have to write it's a square. Okay. That means we can write C1 V1 plus C2 V2 whole square. And we can write here C1 plus C2 whole square. Now this C1 plus C2 and this is square can be cancelled out. Okay. And here we are left only with C1 plus C2. Here we have to apply the formula A plus B whole square. So let's see what we get. We get UF is equals to 1 by 2. This C1 plus C2 is gone. Here in bracket we can write C1 V1 C1 square V1 square. Okay. Plus C2 square V2 square plus 2 C1 V1 C2 V2. Okay, that's what we get. And what we are having in the denominator, it is C1 plus C2. Okay, and let us mark this equation number 6. So we got the expression for final potential energy stored in the combination of two capacitors or in the system of two capacitors. Okay, so this is the final potential energy. And what was the initial potential energy that you have written in equation number 5? Okay, what was that? Half was taken common. Inside the bracket it was C1 V1 square plus C2 V2 square. That was there. Okay. So now we have to find out the difference in potential energy. Okay, or change in potential energy. So I have to rub this. Just note it down. Note it. Okay. Now we have to write the change in potential energy. Change in potential energy. Potential energy. Now, change in potential energy is what? Obviously, U final minus U initial. That's what we write change. And change is written by delta U. So what? Now we have to write the value of UF and UI. Okay. So we can write here like this. Delta U is equals to, first we have to write the value of UF. UF is this much. That is half inside the bracket C1 square V1 square plus C2 square V2 square plus 2 C1 V1 C2 V2. Okay, that's all upon C1 plus C2. Okay, that's what we are having initial. Final minus initial minus what is initial? Half C1 V1 square plus C2 V2 square. That is there. Okay. Now from these two we can take half common. Okay. So first thing which we have to do, that is we have to take half common. And when we are taking half common, then we can apply a square bracket. Okay. I have applied a square bracket. Here delta U is there. Now see, we can take the LCM C1 plus C2. If we want to take the LCM C1 plus C2, we have to multiply the C1 C2 with this. Okay. So what we can do, see here, C1 square V1 square plus C2 square V2 square plus 2 C1 V1 C2 V2 minus C1 V1 square plus C2 V2 square into C1 plus C2. That's what we have to do, because we have taken C1 plus C2 as LCM. Okay, we can close the square bracket. That's what we have got. Sorry, the square bracket should be on full. Okay, this we get. Can you see it? Now we need to multiply these two. Okay, so when we multiply, let's see what we are going to get. See, it is little bit no tedious job is there. Okay, but we have to do. So it is C1 square V1 square plus C2 square V2 square plus 2 C1 V1 C2 V2. Okay. Now, when you multiply C1 to this, what you will get? C1 multiplies to this, then C1 square, and V1 square is already there. So we'll get C1 square, V1 square. Minus sign is there. So minus C1 square, V1 square. Now you multiply this C1 to this. So C1, C2, V2 square with minus sign, minus C1, C2, V2 square. Okay, C1, C2, V2 square. And minus sign is here. Okay, that's all. Now we multiply with C2 because this part is over. C2 into C1. So we will get C2, C1, V1 square with minus sign. So minus C1, C2, V2 square. Now when we will multiply this C2 to this, what will we get? C2 into C2. C2 square, V2 square with minus sign. So you can write minus C2 square, V2 square. That's what we will get. And now denominator is what? C1 plus C2. Okay. So we got this now. Now see, we have to check the terms which are going to cancel, because I know. Just see it once, then we will cancel. Okay. Now here C1 square, V1 square is there, plus here C1 square, V1 square minus is there. Okay. Here C2 square, V2 square plus is there. Here C2 square, V2 square minus is there. Okay. That can be cancelled. Now what is left? We are left with this, this and this term. Now just see what is common in all the three terms. It is C1, C2. Okay. So if we can take C1, C2 common, what will we get? See, we are going to take minus C1, C2 common. If we are taking minus C1, C2 common, so we will be left with, see, if you are taking minus C1, C2 from this, minus C1, C2 you are taking common, what is left? V1 square. So you can write V1 square. If you are taking minus C1, C2 from this, what you will get? Plus V2 square. So plus V2 square. If you are taking minus, first minus C1, C2. So it is already plus. If you are taking minus common out of it, what you will get? A negative sign. So C1, C2 also you are taking, so you are left with minus 2 V1, V2. So minus 2 V1, V2. That's what you will get. Okay. And in the denominator, what you are having? You are having C1 plus C2. That's what you are having. You can see it. Minus C1, C2 is common. Then you are having V1 square plus V2 square minus 2 V1, V2. Now tell me, this is falling under certain pattern. Is it falling in some formula? Yes, it is falling in the formula of A square plus B square minus 2AB. Okay. So we can write the formula. Just I have to write this. Okay. So what we will get? Delta U is equals to, we are going to have this minus, okay, out. So minus, it is C1, C2. This is what? This is obviously V1 minus V2 whole square upon 2 C1 plus C2. That's what we get. You can check it. Okay. Now, have you heard that capacitance is even negative? No. So what we can write? As V1 minus V2 whole square is greater than 0 and C1 is greater than 0. Also C2 is greater than 0. Okay. Therefore delta U is negative. Okay. Negative, or what you can write? Delta U is less than 0. Because negative means less than 0. Okay. Now what will happen? When this delta U is negative, that we can see from here. The difference in energy is coming this much, no? Minus sign, what it is indicating, just see, because delta U is negative. So what is meaning of delta U is negative? That means delta U is what? UF minus UI. That is less than 0. When this is less than 0, so UF is less than ui. That's what it means. That means final potential energy of the combination of two capacitors is less than, or two conductors is less than the total initial potential energy of the two capacitors or two conductors. Okay. So when initial is more and final is less, what does it mean? The energy has gone down, it has decreased, there is a loss of energy. Okay. Hence, there is loss of energy. Okay. That's what we get the result. Hence, there is a loss of energy. How much energy has been lost? This much. That is C1 C2 in bracket V1 minus V2 whole square by 2 C1 plus C2. This is the loss of energy. The energy decreases by this amount. Okay. See, let us take up a question. Okay. And this question was asked in Turkey. It is there now, you know. That. Now see, what is the question? Question is that there is a capacitor of capacitance 0.1 farad. Okay. And now it is connected to a battery of potential difference 10 volt. Okay. And it is charged. And when it is charged, it is disconnected from that. Okay. And when it is disconnected, then it is connected to a, now when it is charged, then what is charge on the capacitor? See, charge is Q is equal to CP. C is 0.1, V is 10. So how much charge you are going to have? Obviously 10 into 0.1 is 1 coulomb charge you are going to have. Okay. Now the question is that now what happens now? This is disconnected from the battery, the capacitor is disconnected from battery. Okay. And it is connected to another similar capacitor. Okay. Such that the distribution of charge takes place equally. Okay. There is an equal distribution of charge between two capacitors. Means half charge is with that, half charge with this capacitor. Okay. So both are equally getting the charges. Okay. So suppose here 1 coulomb charge is there, so half coulomb charge one will get, half coulomb the other capacitor will get. Now what they are asking, what is the final potential energy? Okay. So that means capacitance of both the capacitors is same. Okay. That's why they are getting the equal charge. So rather we can write it C1. Okay. That will be more better. Okay. So obviously C1 we can write. Okay. Okay. And we can write it let it be V only. Okay. No problem. The second capacitor has got capacitance how much? 0.21 because that is similar capacitor. Now when they are getting equal charges, that means what is charge on each? So charge on each capacitor is how much? 1 by 2 coulomb. Okay, that you can write like equal to small q. Okay. Now what is the total energy? Final total energy. Final total energy is obviously half. Okay. Which formula is better to use? Obviously, okay. So we have to use the formula half q square by c. So q square by c1 for first one. For second one, it is half q square by c2. Okay. But c1 is equal to c2 is there, no? So no problem. We can write it as no. Okay. As better we can write C only, okay, for both because both are equal. So why to write C1 C2? It's better C, okay, because capacitance is same. So here we can write 2 q square by 2c. Okay, so 2 cancels out. We'll get what? Q square by c. Okay, q is how much? It is 1. 1 square by c is how much? 0.2. Okay. So 1 square is 1. 1 by 0.1. That means you can write 10 by 1. That is 10 joules. That is the energy stored. Okay. Understood? Very nice. So first part we have done. We have got the final potential. Now we have to find out the ratio of final potential energy to the initial potential energy. Okay. Okay. So should I rub this now? Okay. Is that correct? See, Q was how much? Q was half coulombs. How can I write 1? You have to write here half. 1 by 2 square. Okay. So 1 by 2 square is how much? 1 by 4. So it is 1 by 4. So 1 by 4, and here we are getting 0.1. So for this 0.1 we can write it 10 by 4. Okay. 10 by 4 is how much? That is 2.5. Okay. Now it is correct. Correct energy is how much? 2.5 joule. Okay. Because 2.5 for your 10. Okay. Now we have to find out the initial potential energy for that. Initial potential energy is half CV square. Now half C is how much? 0.1. V is how much? 10. So square of 10 we have to use. Now what we are going to get? Half into 0.1 into 10 square is how much? It is 100. Okay. So it is 100. So what we can do? First we will multiply 0.1 with this. So what you will get? We get into, that is 10. 10.0. Okay. Now you can cancel with this. 2 5 ja, 2 1 ja. So what you will get? Initial energy is how much? 5 joule. Okay. Initial energy what? We got initial energy. Initial potential energy is 5 joule. Okay. Now what we need to do? We need to take the ratio of final to initial. Okay. So let us do that. U final upon U initial, and that is 2.5 upon 5. So 2.5 1 ja, 2.5 2 ja. You get out 1:2. That's our ratio. Okay. Okay. Our next topic is dielectrics. Okay. Actually, students just keep on wondering what is dielectric. Okay. The chapter is completed then also. See, actually, dielectric substances, actually these are the non-conducting substances, or we can say that these are the insulators. Okay. Let's go to the definition of this. Okay. A substance which does not allow the flow of charges through it. Obviously these are the insulators. Okay. That's why they don't allow the flow of charges to them. Okay. They are not conductors, but can be polarized through a small localized displacement of its charges. Now, are there charged bodies? No way. See, they are simple neutral. Okay, we can say simple neutral insulators. Then what does it means? Okay, through the localized displacement, small localized displacement, they can be polarized. What does it means? Displacement of their charges. Okay, so which charges they are talking? They are talking about the charges which are there in the atom. Okay, atoms have got, the electrons revolving around the nucleus, and the nucleus which is positively charged. Electrons are negatively charged. Okay, so what happens now? When you place them in an external electric field, so what will happen? In electric field, the electrons experience force in the direction opposite to the electric field, and the nucleus will feel a force in the direction of electric field. So your atom, which was almost spherical, gets deformed, and when it gets deformed, so it starts behaving like a electric dipole, because the amount of negative charge and amount of positive charge is equal in an atom. Okay. So when it gets deformed, all the electron cloud is near here, so you will get all the negative charge here and all the positive charge is here, so it behaves like a electric dipole. Okay, clear? So this is called polarization. When this two polarities are developed, this is called polarization. Okay, and that occurs. Clear? So even they are insulators, then also they can be polarized when placed in the external electric field. Got it? Okay, so what are the examples? You can note out just write the definition and then write the examples. Okay. For example, glass, water, wax, rubber, stone, plastic, and wood, okay, etc. After that, so these are the examples of dielectric substances. Okay, it can be adjusters also. So these are the examples of dielectric substances which do not allow the flow of current through them, but they get polarized when they are placed in an external electric field. Okay. Okay. See, dielectric substances can be categorized into categories. One is non-polar dielectric substances, another is polar dielectric substances. Okay. Now, what are non-polar dielectric substances? Please put that in non-polar dielectric substances, and then you can write the definition. Okay. Started. Okay. Thus, dielectric substances in which the center of mass of positive charge and center of mass of negative charge coincides are called non-polar dielectric substances. Are called non-polar dielectric substances. Full stop. Now see, what are their properties? Okay, so write in that these have their own electric dipole moment, comma, they behave as an electric dipole. No, they don't have, sorry, you write, they don't have their own electric dipole moment, okay, and comma, they do not behave like an electric dipole. Why? Because see, center of mass of positive charge and negative charge is coinciding, so they will not behave as a electric dipole. Now see, what are the examples? Let me give you example. Let's see H2. See, when you see the molecules of H2, what you will find? Suppose this is H and this is H. This H2 is formed due to the sharing of electrons between this hydrogen atoms, okay, and both are the hydrogen atoms. So there is no difference of electronegativity between them, okay. So both are trying to pull the shared pair of electron with equal force. So the shared pair of electron will remain here only, okay. It will neither shift this side nor it will shift that side. So it will remain here only, okay. And thus neither this hydrogen becomes positively charged nor this hydrogen becomes positively charged, because whoever pulls the electron towards it becomes negatively charged, and the atom from whom the electron moves away becomes positively charged. But here it is at the center, so no charging at all. So it is not going to act as a electric dipole. So it is a non-polar dielectric substance. Okay. In the same way, we have got other substances like O2. Here O2 is another example. Okay. They also share 2 electrons with each other and they form O2. That is again non-polar. Okay. Even we have CO2, like CO2. See, again between carbon and oxygen there is a less difference of electronegativity, and that's why what we find CO4. Okay. So center of mass is at the center of carbon of the negative charges as well as positive charges. So what happens? It remains neutral. Neutral means this is also neutral. Both are neutral. Neutral. No, we cannot say, that's not an appropriate word. Appropriate word is that it is not going to behave like an electric dipole. Okay? And that's why it is also an example of non-polar dielectric substance. Okay. Now, next you put the heading polar dielectric substances. Written. Now start writing the definition. The dielectric substances whose center of mass of positive charge do not coincide with the center of mass of its negative charge are called polar dielectric substances. Full stop. Then you write in that only, okay? They have their own electric dipole moment, comma, they behave as an electric dipole. Full stop. For example, now we are going to take the example, and it's a very famous example, no? I think we are using water every day. It's very essential for us. So what is the formula for water? It is H2O. And if you're talking about this, so you can say like this: O, and here hydrogen is there, here also hydrogen is there. And they form by sharing of electrons. O is at center. Sharing of electrons. This also shares one electron, this also shares one electron. This shared pair of electrons, okay, and here also the electrons are shared initially. These pair of electrons are pulled by the oxygen towards it, okay, and these electrons shift towards oxygen, and due to that the oxygen gets a negative charge, partial negative charge, and hydrogen gets partial positive charge. Now you tell me, this is going to behave as a electric dipole or not? Obviously. And here also, due to this also, it will get a positive charge, and here it will get. So you can write like this. You can write like this. Okay. This is a dipole, electric dipole, and this is again another electric dipole. Okay. So there are two electric dipoles, and obviously when electric dipole is there, then it will have its electric dipole moment also. Okay. So that is the characteristics of a polar dielectric substance. H2O is the example of that. Okay. Not only H2O, but even if you are talking HCl, because see, the electronegativity is not same of oxygen and hydrogen. Okay. Here also hydrogen and chlorine, you can see the chlorine at the last group, 17th group, no, and hydrogen in the first group or just above the first group. Okay, it is placed isolated, no. So there is a huge difference of electronegativity. So when this hydrogen and chlorine share the electrons, what happens? No, this shared pair of electron is dragged by the Cl because it is more electronegative. As the electron is dragged towards it, so it gets partially negative charge, and this gets partially positive charge because electron pair is moving away from it. Okay. Now what they are forming? They are forming an electric dipole. And when they are forming an electric dipole, then obviously they will have an electric dipole moment. Okay, clear? So these are the polar dielectric substances. Understood? Okay. With this, thank you, my dear children. In the next video, we will discuss about the other things, okay, other topics. Till then, take care, keep on studying. Bye-bye.